Alright, so let me start by fulfilling a long-hauled wish of Rappaport. You will see. Namely, let me recall the different incarnations of Stukas over an algebraically closed field. And I should have started by fixing C over QP in algebraically closed field. So the first Stukas over like the tilde of C was just one paw at this chosen until that we fixed. And I mean, well, I guess it's just a restatement of the theorem of Fark. So pairs T psi where T is a finite free ZP module and xi in T tensor ZP beta rom, meaning beta rom C sharp, or also with a plus.
You mean C?
C, thank you. It's beta rom plus like this. Then this category of Brauer-Kiesian modules over the ring A inf, which is again the one for C. And then there's also yet another incarnation of this category, which is good to have in mind. And that carries the following data. So first of all, so f and f prime are vector bundles on the Fark-Fontaine curve. Beta is an isomorphism between f restricted to Fark-Fontaine curve minus infinity. Where infinity is this chosen c-valued point of Fark-Fontaine curve corresponding to this until, such that f is trivial and then you also need to choose a small extra datum. So then the datum of this vector bundle f is equivalent to a finite dimensional QP vector space, and you need to fix a ZP lattice inside it.
So infinity is any.
Infinity is the one corresponding to this chosen characteristic zero guy. Corresponding. So let me just briefly. So I guess the equivalence of 1 to 3 was proved in the lecture, and let me just explain how 4 is related to the other guys. So if you have a Stuka, say, then this lift over. So here we get the locus where p is equal to 0. Here again we get the locus where p flat is equal to 0. Then here we somehow had the point with residue field C and so on. And y0 infinity was this locus here. And that's where Stukas live over. And you can restrict the Stuka either to this part. So here E phi E restricted to y some r infinity. So there this will be an isomorphism, and this gives rise to a vector bundle f prime over the Fock-Fontaine curve. And you can do the other thing where you restrict to some, you don't include 0, but you otherwise restrict some neighborhood. So if you take here E phi E restricted to y0s, then again this will be an isomorphism. And gives rise to f prime over this curve to f. And generically, these two are isomorphic while applying a power of Frobenius. But at this one point, something happens which gives rise to this modification here. And on the other hand, we also have to extend over the puncture p equal to 0. And as I recalled last time, this works precisely when f is trivial. In that case, you have to give an extra datum, which was the CP lattice. And if the paw is such that, I mean, in some sense minuscule, more precisely, is such that a uniformizer times the standard lattice is contained in psi, is contained in the standard lattice. Then these are also equivalent.
So there's a meromorphicity condition on
Yes, the Stukas was meromorphic for. I guess I should have included it in the definition from the start. And then these categories are equivalent to p-divisible groups of OC.
Actually, I was thinking more about this beta. So if you look
this beta is an isomorphism on the algebraic guy. The straight means the algebraic guy.
Oh, sorry. Okay.
Okay.
It would be the same to have a meromorphic guy and isomorphism on the analytic guy.
So you could get an equivalence between 1 and 4, you say, if if I put the analytic guy here and make both non-meromorphic, potentially, yes, that's right. Okay, and so in these moduli spaces of such guys, what we're doing, for example, in this picture given by 4, is we fix f prime from the start as this vector bundle corresponding to some sigma conjugacy class. Some of the isomorphism class of f is also fixed because for all Stukas this has to be trivial. And then essentially what we're parameterizing is such isomorphisms here, such modifications. And that will be the theme of today's lecture, more or less. So back to modular spaces of Stukas. So fix the group is just GLR as before. I fix a sigma conjugacy class B and BFG, and
so this psi is the usual psi from B neuron plus.
This is the usual psi from B neuron plus. So that's a uniformizer. B neuron plus. And some conjugacy classes of core characters. And so let me actually also assume that this characteristic P algebraically closed field that I'm considering is FP bar. And then I guess I'm using interchangeably the notation QP brev and L for the ring of bit vectors and vert P. And let me also represent the sigma conjugacy class B by some fixed element in G of L. And so then we get this fixed vector bundle, so EB phi EB over y0 infinity for like any y infinity of any perfect ordered algebra, where the vector bundle is just trivial, so it's just O to the R on this space, and phi for EB is G times the phi for the structure sheaf. Okay, and so let's recall the definition from last time. Stuka for G of R, B into i's to so it's a functor which takes a perfectoid K algebra R plus with n untilts Ri sharp over QP breve, which then give rise to inclusions xi from the adic spectrum of Ri sharp plus into this y infinity, y0 infinity for R plus. I guess strictly speaking, that's what I call the graph of the points xi. To the set of Stukas E phi E over the sky, Stuka over R. Pause only at the xi in a way which is bounded by these co-characters in a way I made precise last time, plus an isomorphism between this vector, this varying Stuka, and this fixed guy near the boundary. Okay. And so far this is just any functor, but actually it is a sheaf on the faithful side. Okay, so let's think about what we have to prove there. So we certainly have to prove that we can glue this vector bundle E here. Once we have glued that, then some of the gluing is some equivalence of descent data, then the phi E also descends. The boundedness condition and that there are only poles at the xi certainly descends. And this isomorphism similarly descends if you have this descent of vector bundle. So the only non-trivial part is really to descend this vector bundle E. So. And I want to reduce this to some gluing of vector bundles over perfectoid spaces, but this guy here is not itself perfectoid, so I have to make a small reduction first. So recall that this in some sense pre-perfectoid, so more precisely if I take this guy, so it just lives over the adic spectrum of ZP. But I can extend scalars to some perfectoid fields, say the cyclic atomic extension, doesn't really matter. I guess in class I was using a slightly different one there. That makes sense. That guy is perfectoid. And whenever I have a faithful cover of the adic spectrum of RL plus, it induces a faithful cover of that guy. And so if I have a vector bundle E, then this gives rise to a vector bundle on the base change, so meaning this completed tensor product. But actually, you can somehow cut out E again from this completed tensor product using an idempotent. And so it gives rise to somehow E, which is one tensor and idempotent on ZP cyclid.
What's this idempotent?
Well, it's just an idempotent in the endomorphism of an algebra of this gadget. It's somehow not an idempotent over the ring, it's just...
Oh, so you're splitting off as a module.
I'm just splitting off as a module over the smaller ring.
Sorry, can you explain that again?
This idempotent is just an idempotent in the endomorphism algebra over the smaller ring, somehow for this gadget here.
Okay.
Oh. So that's a projection. So that's a splitting of the obvious inclusion. And so if we can glue this completed tensor product, then we can also glue then also E glues. Because for the kind of covers we're taking, we're only making covers here, which somehow preserves linearity of this part. And so that part will also glue. And so then also this bundle E will glues. And so that's reducing
you
us.
also want to make sure that what you're glue, this thing that you get when you pull back is still
as a
still
vector
bundle.
bundle. Yes.
And
So let me write down the statement I want to prove, which probably makes it clear. The lemma we need is the following. The association, which takes any perfectoid Hoover pair, not necessarily of characteristic P now. Yeah? So this guy is really not of characteristic P. To finite projective R modules is a sheaf on the faithful side, or is a stack on the faithful side. Meaning you have descent for all surjective maps. Okay.
I give you a sheaf of modules and I tell you that it's drawing some vector Hoover pair and I tell you that its pullback along a faithful cover becomes a vector bundle. You know that it was a vector bundle in the first place.
I don't claim this.
Okay, really? Okay.
Well, it might.
Just the problem that maps aren't flat.
No,
Yeah, it's not so clear. I mean, there could be some junk part which just goes away after a faithful cover. Probably there is not such a junk part.
The only reason I'm asking is if you start with something after going up to this ZP, tensioning up this thing,
Yes.
and then you pull back, the thing you're pulling back along has nothing to do with the ring map. But you still want to kind of bundle. Anyway, somehow logically after the level, so I guess.
I guess what I have to prove is that if I have some module over this guy here, whose base extension to here is a finite projective guy, then it was a finite projective.
Right.
Or you have a splitting.
I think that should be okay because the situation is so simple, but yes. I should check it at home. I mean, you have to be slightly careful at this point, but I think it should be okay. Okay, so let me recall what we have to show. So that for it's tilde some spar or tilde off. Projective. The functor from finite projective R modules to M to finite projective R tilde modules M tilde plus a descent datum as an equivalence of categories. And it's essentially it is fully faithful. That's because you can recover the module as the part of the module which is somehow invariant under the descent datum, and that follows from the sheaf property for the structure sheaf. So. And so this means that if you want to glue, we can do it locally. So. I mean, essential surjectivity can check locally. As vector bundles glue over open covers by k.edu. Okay, so we have to do this locally. And so actually let me first do the case where there's just a point. So where let's put k is a non-convenient field. And then actually the usual proof of descent works. So the point is that in that case, tensoring within complete tensor product with a k-Banach space preserves a cyclic complex of k-Banach spaces and detects a cyclicity.
even if the K bar space isn't countable type?
Well, I mean, any completed tensor product with an uncountable guy is still the algebraic direct limit of all the completed tensor product with countably generated guys, because like any element is a completionist somehow, you need only countably many elements to approximate it, and so you can formally reduce to the countably generated case actually. So let C be a complex of Banach-Kivicke spaces. And V not equal to 0 is some Banach-Kivicke space. Then C is a cyclic, if and only if. It's not so hard to check. So what you have to use is what I just said. So use W tensor complete tensor product with V is the direct limit over all V prime and V, which are topologically countably generated of W complete tensor product with V prime. And if V is countably generated, then it has a topological basis. Okay, so this means that at a point we're fine, and so now consider the general case. So in general, we want to descend some tilde, and let me actually assume it's free, and you can do that. So you may assume that M tilde just as an R tilde module is free. Just by replacing R tilde by some open cover. So X tilde by some open cover. Over which the module becomes free. And so then the descent datum is given by some matrix B over the fiber product, so over R tilde completed tensor product with R tilde, which satisfies some relation. So it's classical. Okay, and we know that so it's enough to descend locally, so let's pick any x and x. And so it has some complete residue field k of x. And we know that we can descend the pullback to k of x. So. And in terms of this matrix description of what's happening, this means that we can somehow change bases in such a way that somehow the basis becomes invariant. So in other words, there exists A at this point x, which is a matrix over R at the fiber x, such that as somewhere in the fiber over X, so meaning in this completed tensor product is K of X. This is just first projection pullback of AX times second projection pullback of AX inverse. Okay. Okay, so we can spread this matrix, we can approximate this matrix by some matrix defined over a small neighborhood. So we can.
So what's the claim about B such that B equals this belongs?
As an element in here. So I mean B is a priori element in this guy, but
sorry,
that's
sorry,
something
B,
in here.
Sorry, B is B. Okay,
Yeah.
sorry,
Can approximate AX by some AU, which lies in QR times OX of U.
So A parenthesis X is the same as A sub X.
Thank you, yes, it is. Somehow such that the image in there is somehow p-adically close to this guy. Just because some of the algebraic tensor product stands in the completed one, and OX of U, the direct limit, stands in K of X. And so after conjugating by A of U, we may assume that B actually has integral entries, because that is certainly somehow after conjugating it has integral entries at x because there it's 1, or because I just approximate maybe just close to 1, and then also in the neighborhood, so it can ensure that it lies in this guy or x plus of U. And actually, maybe that it's even congruent to 1 mod some pseudo-uniformizer pi there. And so we are allowed to work locally, so we may replace x by u. And so we can assume that B has these properties to start with. So in other words, the spaces that we now have of tilde is maybe not invariant under the descent datum, but at least mod pi is invariant under the descent datum. And now we want to adapt the basis further so that it becomes invariant under the descent datum modulo higher and higher powers of pi. Okay. So, but what happens is that if you look at b minus 1 over pi, then this gives a.
So this pi is the one that's coming from like R?
Pi is any pseudo-uniformizer in R, yeah.
But the approximation is coming from the lifting from the residue field, right?
Yes, but if something is 1 mod pi over in the fiber over X, then it's 1 mod maybe slightly smaller power of pi in a neighborhood.
Oh, sorry, everything is perfecto, right?
Well, no, that's just adic spaces.
No,
Because some of the loci where these elements are close to 1 defines an open subset.
I'm just saying you can get arbitrary close to the full maximal ideal.
Ah, yeah, so I can replace pi with
Yeah.
root if I want to. And so if I look at b minus 1 over pi, that's now has integral entries still. And I can look at mod pi, and the multiplicative co-cycle condition on b becomes now an additive co-cycle condition here. So there's a change co-cycle for the covering of x tilde over x with coefficients in x plus 1 pi. But this is almost 0. And so this means that we can conjugate b such that b minus 1, maybe it's not congruent to 0 mod pi squared, but at least mod pi squared minus any epsilon.
H1 here means matrices that find R over H1?
Sorry, I guess I have to put MR on this. Yes. Yes. And so this way we can increase this power of pi, and so then just continue. And so in the limit. And then we're done.
Because the ring is formal or?
It's p-adically complete. Everything's p-adically complete.
Pardon me?
Everything is p-adically complete. Okay, so that's a funny doing statement. All right, and so the theorem I want to prove in this and the next lecture is that the space of Stukas is actually a diamond. And that's probably the main theorem of this course. So it's probably a priori not very interesting, but at least it means that there are some spaces which have some atomic homology groups that might be very interesting to study.
And is the theorem known to be true more generally beyond GLR?
Yeah, I think the issues are like not so. Yeah,
Okay.
yeah.
Don't ask that question now. Don't need that question
now. So the strategy is the following. So first we define a period map. Let's still call it a Grothendieck-Messing style period map, which goes from the space of Stukas. To some Bayesian and Greenberg-Grassmannian, which I will introduce later. So it will live over n copies of body QP breve, and will maybe be bounded also by these mu parks. I will give a definition later. So what this does is just that this period map just records the modifications happening at the points, recording the. And so in the case of this modular space of Peter-Wieser groups that we had last time, this was just some usual Grassmannian. But in general, it's something more fancy because we have to parameterize some Biedermann plus lattices. The second step then is to prove that the target of this map is representable. that I will do next time. No, I'm putting some bounds here, so it's actually then. And so, and there's a version of the theorem I stated in the very beginning, which works for several pawns, and so Stuka is the most information is just these modifications, but then there was this additional requirement that one of the two vector bundles should be trivial, and also you had to fix some lattice there. And that's kind of extra information we still have to take into account. And so, but first of all, so using the modification, we can build over all of the target. We can define some guy over the guy away from 0 by modifying this fixed guy. So then the image of the Grothendieck missing period map will be the locus where E prime near the boundary, so restricted to y0s, s small, so small that phi is an isomorphism there, is trivial. Okay, so we have to understand this locus.
You mean trivial on the geometric points?
On the level of geometric points, yeah. And locus of the geometric points. But actually you can show that where this happens at the geometric point over some point, somewhat only depends on the point inside the space. It really defines the subspace of the topological space underlying this. And so let me call this locus the admissible locus. The notation is becoming quite bad, but anyway. So you have this Grassmannian which parameterizes the filtration, and there you have this admissible locus where this vector bundle is trivial. And now there are two very non-trivial theorems in the paper by Kedlai and Liu. The first of which says that this is actually an open subspace. And open subfunctors of diamonds are also diamonds. Is there also an analog of weakly admissible? I don't think so, no. Well, the issue is that here we're really parameterizing stuff in... so weakly admissible just refers to a filtration on the usual vector space. And such a beta-1 plus lattice gives you such a filtration via this, what's sometimes referred to as the Spialinitsky-Birula map. Where you just look at the intersection with various translates by the uniformizer. But this map is not an isomorphism outside the minuscule range. And I think this weak admissibility, if you formulate something, would only be something on this usual flag variety, whereas here we're really doing these bigger things inside the F1 Grassmannian. So I don't think there's an error. Nonetheless, if you're trying to understand classical points, there might still be like a description of, like if you have a classical point in some sense of this Grassmannian here, which is probably just a point with values in the spar D of some finite extension of QP. It makes sense. Then you can describe whether it lies in the admissible locus by some analog of weak admissibility. The issue is that on classical points, there's a unique Galois covariant section from this smaller classical flag variety to this more fancy. I'm not sure if this made any sense to anyone.
But I guess on non-classical points, it's not even clear that, I mean, maybe not even true that the fibers of this map from the Grassmannian to the filtration thing is that sort of whether or not you're admissible is even constant on those fibers.
That's right, that's right. So what happens like for classical points, but is that there's a unique section of this, and then you can ask at that point. More generally, like, so there's this map from Strada of like Schubert open Schubert cells of like just assume there's just one pair, yeah, of this B1 plus Grassmannian to a classical flag variety. Which is a Spialinitsky-Bura map, and whenever you have something in here, some classical guy, classical smooth rigid space, over QP Brave maybe, which maps to here in such a way that it satisfies Griffith's transversalities, this map. Then this lifts in a unique way to up here. And for a point, checking Griffith's transversality is vacuous, so there's like always this unique point. But other than that, you somehow don't usually get a section of the whole flag variety because it doesn't always satisfy Griffith's transversality. And I guess if there is a section, it also has the image has to satisfy Griffith's transversality. So the existence of this map is equivalent to Griffith's transversality. But Proits are locally, so there are no differentials, and so there is no Griffith's transversality, and so you can talk about like any family which may not satisfy Griffith's transversality at all. Okay, so that's the first theorem they prove. And more generally, they prove that some of the Newton point of this guy is semi-continuous in some direction. But that's the locus where the Newton point is just a zero constant, and so it gives you an open substring. The second theorem is that over this locus you get a QP locus system. Meaning a sheaf of QP modules which is locally free of finite rank. Where QP is some of this associated to this locally profinite set QP. Let's call this script V, or no, script. Boldface V of rank R over this admissible locus, which is given by the phi invariant sections of this E prime near the boundary. And then also the possibilities of extending of E prime phi A prime to all of it, restricted to like this open part, and then to the whole thing, are 1 by 1 bijection, are the same as the p lattices. Let's call it L, where L maps to L tensor ZP. Yes, makes sense.
So is reusing the specified trivialization?
No, so like if you have something contained in B, then if you tensor it with this guy, it's the most sub guy of E prime, right?
Oh, in B, sorry.
Characterization of this V?
Of what thing?
Of V.
Of V. Well, well, I mean, if you have a trivial vector bundle near the boundary, then it's somewhat equivalent to finite dimensional QP vector space over a point at least. Those are all the fibers. But I mean, the recipe is just always given by taking the phi invariant sections.
And Peter,
Yeah?
there's one value of S that you use over the whole first line?
Yes, all this whole story is independent of S. You can also take the direct limit over all S and work with some robber ring if you want to.
But for any like fixed affluent of some S.
You only have to check the S in such a way that the phi is an isomorphism. And then different values of S are always identified.
Yeah, I guess you just avoid the pause.
Yeah, you just need to avoid the pause. Thus, what is the space of Stukas? It's just the space of ZP lattices in this universal V over the admissible locus in the Bennington vector model. And so I claim that from this description you actually see that this Grotnik messing period morphism from the space of Stukas to the admissible locus of the space in Greenfeld Grassmannian is état. Why? So this can be checked locally. Locally. On the target, say. And so, because a QP locus system can be trivialized there, so we can assume, so without loss of generality, this V is just QP to the R, and then the set of ZP lattices and QP to the R is just the discrete set which is this quotient. So locally, this is really the fibers are just joint QP modulo NZP. So assuming that we already proved that this Gradients-Greenberg Rosmanian is a diamond. Also, space of Stukas. Yes. Because something gets all over the diamond is a diamond. Okay, so that explains the strategy. And so what I will do in the remainder of this lecture is give a definition of the space in Greenberg Rosmanian and construct this period morphism. And then next time we still have to show that the space in Greenberg Rosmanian is a diamond. I can also make the remarks that now we can easily understand what it means to put level structures on the sky. Just trivialize. This ZP local system L mod. Not N. M. Okay. Okay, but now to the definition of the period morphism. Yes, I guess that's will also be defined in the course the process. So for simplicity, let's actually just work over not all of the base spotty QP to the n. But over a certain open subset, where it never happens that one point is a proper phi translate of another point. So it is allowed for 2 points to collide, but just if they really collide and not if one is the phi translate of the other. Otherwise, we actually have to slightly change the target. So you'll see in a second why I'm doing this. So in particular, if you're just interested in the case of one pole, then this issue doesn't come up. Okay, so let me define this Greenberg Rosmanian. And actually, it can be defined over n copies of ZP. And let me also put these boundedness things here. So it lives over n copies of spy ZP to the n. So as a function, it can be defined there. So with n points of spotty ZP, meaning n unfolds, Ri sharp, R, which again give rise to the graph of point x I, which is a closed embedding into the space y 0 and 30.
What's the difference between taking the diamond of ZP or one of QP?
For the QP version, I would like ask that this is really of characteristic 0, the piece invertible here. But if it's over ZP, this might just be the same, just R itself. But in all cases, these points still live in this space. If they were over QP, they would live in the space with like 0 emitter. 2. Assume some vector bundles, so let's call them G. Y 0 infinity R plus the vector bundle of rank R plus an isomorphism between G and the trivial vector bundle away from those points. G restricted to y 0 infinity minus the union of the graphs of the x's with the trivial vector bundle over y 0 infinity minus the union of the x's. Such that the relative position is bounded by mu. With the same convention about colliding points as last time, namely that you have to add up the corresponding mu I bars. So.
That was a condition at geometric forms.
That was it. Yes, sure.
Okay, so the same here.
Yeah. This definition of being bounded by mu I is exactly the same definition as last time. But in particular, I wanted to stress this convention about colliding points because when I say this, it's really not clear that I mean this. I don't know a better way to state this. And so we already checked that we can glue vector bundles, so we immediately get now the proposition that this is a sheaf on the faceless side. And so what I will prove next time.
So how do the untilts relate to faithful cover?
Well, I already proved that body ZP is a where I prove then. Well, it's a sheaf on the faithful side.
It is.
It is, yeah. I mean, yeah. Maybe back then I only proved it's a sheaf on the QPF side, but
right.
The same proof works. So the theorem I'm proving next time is that away from the closed point. So the issue with the closed point is that it's not analytic, but apart from this issue, this guy here is a diamond. So the restriction to this body ZP to the n minus a closed point. meaning that not all of the untilts, like there's no point at which all of the untilts are, just that's the characteristic p guy itself, is a diamond. Okay, so let's assume this for the moment. And so we want to construct this period morphism. So now given a point of the space of Stukas, i.e. Some E phi E over this guy pause only at xi, etc. With an isomorphism near infinity. So what we can do is we can just extend this isomorphism all the way. So it won't be an isomorphism anymore, it will have some meromorphic codes. But apart from that we can do this, so we get an isomorphism between and this other guy over this whole open part, but you remove the union of the graphs of all the phi to the minus m xi.
So the m's are non-negative.
M is greater or equal to 0, yes. I should say this. And so what we can do is we can look at the modification that happens from EB at E at all the points xi. And now I want to use my assumption that no proper translates of one point is another point, because otherwise there's something weird happening here. So let me assume that phi to the m so then we can build a vector bundle F over the same space by modifying this guy EB, which by the way was just a trivial guy, over at the xi using the modification given by E at xi. Okay, so then F restricted to y0 infinity minus the union of the graphs of the xi's is still isomorphic to the structure sheet there. And the modifications are bounded by mu I. And so, in particular, near 0, they are again isomorphic. So for S small, F restricted to S. And so this means that we can uniquely extend this bundle over the puncture at 0 in such a way that this isomorphism extends. So we can extend F uniquely, which is on G over all of Y0 infinity. Such that G is isomorphic to all R. And so this defines a period morphism. This defines.
And to go outward, you use the Frobenius again? And to go outward with this trivialization?
No. I mean, I was building this F just from modifying the trivial bundle. I forget about the F.
Oh, I see.
I only, this only records what's happening at the first instance where something's happening and then forgetting about the other parts. Which in particular means that like close to 0 is again just a trivial die. But maybe I should explain how one goes from a point of the Grassmannian and somehow builds the candidate Stuka. So, because then we again have to modify at the translates. So, somewhat conversely, except that we somewhat can't go all the way. So given the point of this Grassmannian, say over this part U where so we get this modification. G of O to the R, which is just over all of Y0 infinity, but sometimes we don't need all this information. And so let E prime be obtained from EB by modifying at all of the translates phi to the minus n. M greater or equal to 0. Using the phi to the minus m g at xi. So I'm modifying it at the xi's, but I'm doing the corresponding modifications at all the translates of this guy. And so this way what I'm producing is an E prime, phi E prime, which lives over just the open part. Whereas phi E prime being an isomorphism away from the xi.
So when you're talking about make like this GXI hat in this relative setting,
Yes. So I mean that's a finite projective module over the speed around plus corresponding to this R I shard. So the point is that whenever I completed some xi, the xi's are all given by the vanishing locus of one non-zero divisor. So you can always apply the Bouvier-Lasso result actually, in its algebraic form to do all the gluing you want to.
And this is somehow okay even if the xi's kind of cross each other?
That's okay even if the xi's cross each other, because then the equation is just given by the product, yes. I think that's okay. I think so. Yes. Yeah. You can just complete along the product of the uniformizing parameters for the individual guys. It's still a non-zero divisor. And
Yeah, I guess you're making one change at a time. Just one xi at a time.
No, you can't do one xi at a time, because you don't have like individual modifications given for, like if the two collide, then you don't have individual modifications given for the individual xi's. You really have to do both at once, but that's okay. Yeah, and so next time I will prove that this balancing Riemann guy is a diamond, and then over it you can somehow construct this E prime, and then we use these two theorems of Kedlai and Liu that the locus where this E prime becomes trivial near the boundary is open, and that over that locus we get a QP locus system, and then we saw that this implies that the small Gauss space of Stukas is also a diamond. And so what's left to prove is this theorem there.
For the usual Bayesian Grassmannian, there's a blow-up which includes information about individual modifications from the...
Well, you can do that, and that's what you would have to do if some of one xi was a phi translate of another xi, xj. Well, I know there are different versions of the space between Grassmannian, so the usual one doesn't include this, I think, but then there are these convolution Grassmannians or whatever they're called, and they include this information. And so you would have to use such a convolution Grassmannian at the points where, at the points I'm not allowing here.
Can you reconstruct the p-divisible group in the Leaves case?
Well, last time I was explaining that the modular space is the same. What do you mean by reconstructing the p-divisible group?
I mean, but you're using this other theory, the classical theory, so to speak. I mean, when you earlier you said that
I mean, how can I identify with the modular space of p-divisible groups if I'm not using the modular space of p-divisible groups to start with?
Construct the p-divisible group.
No, for this I'm using the theorem I stated in the very beginning, right? That these, like, the Stukas are like there are these various incarnations of Stukas, and if you're in the minuscule case, then they're also equivalent to p-divisible groups.
But it also works in families.
Somehow, I don't have to use it. It works in families for this, but I somehow get it as an output.
But you construct a family of p-divisible
I do construct a family in p-divisible groups in the end. Well, but I mean, for this I have to use that there is this modular space which has any top here and so on. Now, I guess there should also be like a relative. So there should be a relative version of the theorem that Barkisi modules are the same thing as p-divisible groups, but I don't think that's written. Or do you write?
Not written, but I think it's so.
Yes. I think it would be very interesting to know. Yeah. I mean, I think Wansu Kim probably has some results like that.
Maybe now, I discussed with Eike now, he told me maybe he could do it.
Okay, well anyway, so there should be also a relative version, but for this you would have to use this Barkisian incarnation in the relative setup.